Okay, guys, any questions before we get started again? Okay, so I'll wait till that gets to 11:40. Okay, so here is a model. So here is a battery, and here's a resistor, and that's the positive terminal of the battery. The little stubby line is the negative terminal of the battery, and you can see that there's a current flowing through this resistor. A resistor could be a bulb, a toaster, or whatever, so on. Okay, so here's a current flowing through the resistor. And we saw that in reality, what's really happening is electrons are flowing in this direction, okay, in the opposite direction. All right, so what this model is showing you is the following, okay. So for now, we'll just think of the current as positive charges flowing like that, okay. So what is happening here is the following. This is from an energy perspective, okay. So here's a useful way to think of it. So here, the positive charges are at a high potential energy, and they come to the resistance and they lose their energy, okay. And they're at the end of the resistor, they're at the bottom of their energy. So you can think of it as potential energy. Okay, so they're at the bottom of the energy hill, and they've come to the negative terminal of the battery. And now what the battery does is it converts some of its chemical energy and takes these charges and increases their energy and puts them there. So that's what the battery did. It converted chemical energy into electrical energy. And then those charges go about and go around the circuit again, okay? They lose their energy in this device, okay? And then the battery takes them and increases their energy again at the expense of chemical energy, okay? So that's a useful way to think about batteries, okay? So they are a store of energy, some other form of energy, and they convert that energy into electrical energy, which is dissipated in a device outside. Okay. All right, so these are resistors. This is a resistor, that's a resistor, that's a resistor. These are all resistors. Okay. So here's a circuit board with a whole bunch of resistors and other things. So here's a chip, which probably has millions of little circuits. That's a capacitor, and so on. Okay, so this is a transistor. There's a transistor. All right, so in this resistor, you see these bands, and what these bands tell you is they tell you the value of this resistor. Okay, so and the way you read them is the following. So you start off at the color which is closest to the edge. So this is where you start off reading. And you see the other edge doesn't have any band. So this is where you start off reading. And the first three bands tell you the value of the resistor. The last band, the gold band, if there is a last fourth band, that tells you the accuracy to which the accuracy of the value. So this is a gold band. If it's a gold band, then this resistor is accurate to 5%. Okay, so that's an expensive resistor. A silver band gives you an accuracy of 10%, and if there's no band, then it's a 20% accuracy. Okay. All right, so now we'll learn how to use this. We'll learn how to read these resistors. Okay, so the bands are brown, green, brown. So let me so the band was brown, green, brown. Okay, so brown, green, brown. Okay. Now you can look up a table and it'll, with each color is associated a digit. Brown is 1, green is 5. I'll show you the table in a second. So the first two bands give you the first two digits, and the third band is you multiply the power of 10 with that color, with that digit. So brown is associated with 1, so the last band tells you the power of 10 you multiply it with. So this is 15 times 10, which is 150 ohms. That's the value of the resistor. Okay. So here is, again, brown, the number associated with brown is 1, green is 5, and again, the last one is brown. So 1, 5 times 10 to the 1. Okay. So for instance, red, black, brown would be, red would be 2, black is 0, 2, 0, 10 to the power 1. So 200 ohms. These are 200 ohms. This is 150 ohms. Okay. Anyway, so that's how you read them. So these resistors are commonly made from carbon inside a plastic cover. So there's carbon packed inside that plastic cover, and there are 2 wires sticking out, which you use. These are the terminals that you use for electrical connections. Okay. So the value of this thing is denoted by those colored bands, and that's what we're saying here. Okay. So for this one, again, this is brown, green, brown, and this shows you the values are 150 ohms. For the first band, brown is 1. For the second band, it's green. So first, that's a digit associated with the first band. This is the digit associated with the second band. And the exponent is associated with the third band. All right, so now we'll talk about energy. Okay, so you saw that the battery converts chemical energy to electrical energy. And what this is doing is the battery is supplying energy to this device, whatever this device might be. This might be an electric light bulb, a toaster, an electric motor, or whatever. Okay. So now the question is, at what rate is the battery supplying energy? The rate at which energy is being supplied is called power. Okay, so the rate at which power is being supplied is the voltage of the battery times the current coming out of the battery. Okay, so the rate at which energy is being supplied is V times I. Okay, so right now there's only one device connected to it. So the rate at which energy is being supplied is the rate at which energy is being delivered to this device. If there were multiple devices, well, we know the rate at which the battery is supplying power, and then you could calculate the power dissipated in each device. So if you want the power dissipated in this device, that's equal to I square R. It's also equal to the voltage across the device times the current flowing through the device, okay? And it's also equal to the voltage across the device, V squared divided by R. And the voltage across this device is just equal to the battery voltage in this diagram. Okay. So anyway, the power supplied to any device is the voltage across it times the current flowing through it, or I square R, or V square over R. Okay. And if this device was a light bulb, it's converting that energy into light, some of that energy into light and mostly into heat. Okay. So for instance, your incandescent bulb is only about 5 to 10% efficient, meaning only 5 to 10% of the electrical energy is converted to light. The rest is converted to heat. An LED bulb, on the other hand, is 90% efficient. So energy delivered by the source to the load is converted to heat, light, etc. So this is the load, This is the source. All right, let's go to the chalkboard. Okay, so the current model, so here's the map of the United States. We have some central power sources, power generating sources like thermal power plants, dams, and nuclear power plants, and so on. And then energy has to be brought to homes and cities and whatnot. So electrical energy has to be transported over long distances. All right, so now let's look at the circuit. Okay. So let's say we're just modeling. So let's say this is the city. You want to get energy to the city. And these are the transmission lines. Okay. So now what we'll do is we'll say this is the resistance of the transmission line. And this is the resistance of the load. Okay. Meaning that's where you want most of the energy to go. Okay. So the energy power being supplied is ICE is V times I, which is the voltage of the battery times the current. It's also equal to the current flowing through times the total resistance is the circuit is the transmission resistance times the load plus the load resistance. So transmission plus load resistance. Okay. So what this equation is telling you is this is the energy wasted along the transmission lines. Okay. And this is the energy that got to the load to your home, okay, which is what you wanted. But in the process of getting energy from the dam to your home, you wasted this much energy. Okay. And in some countries that can, in some places that can be as large as 10%. Okay. So that would mean like if for every $10 you've earned, you're throwing away $1. Okay. And you don't want that to happen. So to minimize this, here's what we do. Okay, so the rate at which power is transmitted from the power generation station is V times I, and then the loss depends on I squared, the transmission line load. Okay, so what we do is we want to minimize the current. When you minimize the current, this term will be as small as possible. You're minimizing losses. And so to make that small, you have to transmit power at high voltages. Okay, so voltage is high, current is low, then this term will be low. Okay, so that's why you want to transmit power at high voltages, and that's what we're talking about here. Okay, so to minimize power losses in transmission, we transmit power at high voltages. So in the US, power transmission occurs at maybe about 800,000 volts. Okay. Again, that's to minimize transmission losses. Again, transmission losses can be anywhere from 5 to 10%. All right, so let's look at this diagram. Here's a battery. There's a positive terminal of the battery, negative terminal of the battery. And this bulb is lit. Okay, again, the same battery. Now this connection is switched, and this bulb is not lit. We saw in one of the original slides that the bulb didn't care how you connected the battery. Okay, so this bulb was lit when the current flowed in either direction. So what is happening here? Okay, in this case, it's the bulb is not lit. It turns out that here's a device. This is called the diode. Okay, and This is the positive terminal of the diode. That's the negative terminal of the diode. The diode lets through current only in one direction. When a positive voltage source is connected to the positive terminal. When the positive terminal is connected to there, the diode is not letting any current go through. Okay. So the diode is like a one-directional gate. It lets current only go through in one direction. Okay. Okay. Now, if you didn't have the diode and you just had this thing, that was just essentially a pure resistance. And if you increase the voltage, the current through it would increase proportionally. Okay. So if you just had this bulb, here would be the current voltage response. You increase the voltage, the current in the bulb would linearly increase. Okay. Those materials are called ohmic materials. When the current is proportional to the voltage, those are called ohmic materials. Here is how the diode responds. Okay. So the diode obviously responds non-linearly. Okay. So what this is showing you is when a negative voltage is connected to the diode, there's essentially zero current. Okay. And even with the positive voltage, the current is zero for low voltage and suddenly it rises up. So for 0.7 volts, the diode is essentially an open switch. Okay. So when the voltage of this battery increases to 0.7 volts, this diode essentially becomes an open switch. For negative voltages applied, this is essentially a zero resistance. It's as if for voltages greater than 0.7 volts, this is as if it's not even there. For negative voltages, this is a shut gate. It doesn't allow any current through it. Okay, so a diode is a non-ohmic device. Any linear response, any device that has a linear response to voltage, that's called an ohmic material. So here are some non-ohmic materials. Well, here are some materials with interesting electrical properties. There's materials called thermistors. You can see that as the temperature rises, their resistance decreases. Okay, so if you place thermistor, so here's the thermistor. Okay. The current in the circuit is voltage is I times R, and current is V over R. Okay. Now you just saw that in one of the diagrams that if the temperature of this thermistor rises, the resistance decreases. And if the resistance decreased, then the current will increase. And the current will increase. Okay. So potentially this material can be used as a thermometer. Let's say you stick this on somebody's forehead. If the temperature is higher, the resistance is lower, and the current is higher. And so the current can be a proxy for the temperature. So, so here's a thermistor whose resistance is sharply dependent on temperature. Here's a copper wire, for instance. For the same temperature range, its resistance doesn't change much at all. So a copper wire cannot be used as a thermometer too efficiently. So a thermistor is a semiconductor whose resistance depends strongly on temperature. Thermistors can be used to measure temperatures. Okay. So here is the graph for most metals. Okay. So what this shows you is it shows you the resistivity, which sort of is proxy for resistance. And as the temperature decreases, the resistivity of the metal decreases. Okay. So as the temperature decreases, its resistance is decreasing and it's becoming a better and better conductor. Now, if you blow this diagram up near absolute zero, what you find is for most materials, even at absolute zero, there's a residual resistivity, okay? Meaning the resistance doesn't go to zero. Okay, so at low temperatures, a nonlinear region exists. The residual resistivity near absolute zero is caused by collisions with impurities. Okay, and it's almost impossible to eliminate that. But well, we'll come to certain interesting materials where the resistance does go to zero. All right, so in semiconductors, here's what this is showing you for semiconductors. As you increase temperature, the resistivity decreases because with temperature increase, the charge carriers increase, the number of charge carriers increase. So this behavior is opposite of this behavior. All right, so that's in semiconductors. Okay, so here are some materials, very interesting materials, something called superconductors. Okay, and here's a graph of, so here's the resistance of this material. This is for mercury. That's where superconductivity was first discovered. And these are extremely low temperatures. This is 4 degree Kelvin, so that's minus 269 degrees Celsius. Okay. All right, so what you find is at these low temperatures, if you decrease the temperature below a critical temperature, the resistivity of this material suddenly drops to zero. Okay. And that has become a superconductor, meaning what happens is the following. Okay. So, yeah. So what happens is the following. So let's say here's a material, you got a battery, and you pass a current through this thing, okay? And now you start dropping the temperature of this guy. And when the temperature drops below the critical temperature, the resistance of this guy has gone to zero, okay? And so what you can do is you can establish a current and then remove the battery, and the current will still keep flowing. Because there's no resistance, the current won't stop, and it'll just keep flowing in the battery forever, in the wire forever. As long as its temperature is below the critical temperature. Okay. So it's like a frictionless surface, and this puck keeps going around and around. The current keeps flowing even without a battery source. Okay, so that's a superconductor. And superconductors have quite a bit of use. They're very useful. MRI machines use superconducting magnets and so on. We'll learn about them. Okay, and so superconductivity was discovered in 1911. And let me show you a graph. So here was a superconductivity discovered in 1911. And so superconductivity can be useful, and so, but to cool materials to that low temperatures, superconductivity was discovered in mercury first, and it became superconducting at 4 degree Kelvin. So the temperature was quite low, okay? So it was not accessible for everyday phenomena. And so we had been trying to increase the critical temperature, trying to find materials with higher and higher critical temperatures. And we didn't get anywhere for about 75 years. You can see that. For 75 years, the best we could do was about 30 degree Kelvin. Okay, and then suddenly things started getting exciting back in '86, okay, when high temperature superconductors were discovered. These were ceramic materials which we thought we'd never tried before. And so that's what that was, okay. So in 1911, superconductivity was discovered. In 1986, high temperature superconductors were discovered. Okay. So using superconducting magnets, fields 10 times stronger than normal electromagnets can be produced. And so that's their use. Yeah. And strong magnetic fields can be used for many things. Okay. So what I'll show you is a brief little video of maglev trains. Okay. And I urge you guys to go see this video later, but I'll show you a brief little clipping of it. So.
One doesn't have to be a passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it. The core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below -183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material. An impressive experiment is designed to demonstrate how strong the forces are which hold the superconductor on the track. The superconductor is brought into a certain distance of a few millimeters above the magnetic rail and cooled down in this position using liquid nitrogen. Reaching the specific transition temperature of -183 degrees Celsius, the superconductor traps the magnetic flux of the outer field. Now we can remove the shim of a certain thickness which determines the distance. The superconductor has now memorized its position within the field of the rail. The superconductor is fixed at this distance and can only move along the magnetic rail even when turning upside down. But the effect lasts only as long as the superconducting state in the material is maintained. To set the superconducting levitation train in motion, one has only to give it an initial impulse by hand. Due to the lack of friction, the steam engine goes round and round until the liquid nitrogen is evaporated and the material warms up. Then the effect of superconductivity ceases, and what has been a strong magnet at low temperatures turns into a ceramic material without particular magnetic properties. Above the so-called transition temperature, superconductors are no longer affected by magnetic fields, and the locomotive drops back to the rail due to the effects of gravity.
All right, so that was superconductivity in action. Okay. And China, in Shanghai, there's been a maglev train operating since 2004, I believe. Okay. So anyway, check out the video, and you can find many such videos on YouTube. All right, we'll give you a quick microscopic model of conductivity again. So you saw that inside a metal, the electrons move about randomly. Okay. You introduce an electric field inside the metal by connecting it to a battery. Now the electrons acquire an average drift speed in that direction. Okay. And in the presence of electric field, electrons, in addition to their random speed, acquire a drift speed of the order of 10 to the -4 meters per second. Okay. So the acceleration of the electron is charge of the electron times the electric field divided by the mass of the electron. You've seen this equation from kinematics. That's the final velocity is initial velocity times acceleration times time. Now we'll take the average final velocity, and the average initial velocity, even though the initial velocity between collisions can be, the speed can be as large as 1,000 kilometers a second, the average value of this is 0. Okay, so when you take the average final velocity, this average of this is 0, the average of this is, these are constant terms, and that's equal to the average time between collisions. Okay, and the average time between collisions is denoted by tau, and that's the mean time between collisions. So the drift velocity is the charge of the electrons times the electric field divided by the mass of the electrons. And this works out to about 0.1 millimeters a second. Okay. And anyway, so this is the current density is related to the electric field like so. That's equal to the charge density times the drift velocity, and you can put in the expression for the drift velocity. And so you can get an expression for conductivity of the material. It's the number of carrier charge density times the charge of the carrier squared divided by the mass. Okay. All right, that covers this chapter. Okay. So what we talked about was electric currents, and the important relationships were, so let's, yeah, so the important relationships were, so we're talking about electric currents. And we saw that here's a battery, okay. Here's a resistance, okay. The current in this was given by Ohm's law, is I times R, okay. The resistance of this wire, or the resistance of the wire depends on the resistivity of the material, length of the wire, and the area of cross-section of the wire, okay. So greater the area of cross-section, lower the resistance of the wire. So thicker the wire, lower its resistance. Okay. And then we saw the power dissipated in this device, okay. So how much power was dissipated in this device, or also the power dissipated in this device was also the power supplied by the source. Okay, the power was given by V times I, or I squared R, or V squared over R. Okay, so if you wanted the power dissipated across this device, you measure the voltage across this device times the current through this device, gives you that, gives you the power dissipated there, or I squared R, or V squared over R. Okay. So those are the concepts we learned from this chapter. And so I'll stop now and I'll open the floor for questions.